Okay, we are going to prove Theorem 0.2, Part 5. So, in case this is the first class you've had where you've had to do quite a bit of proofs, I want to do even a lot of simple proofs. The more you see, the better off you'll be. And this is a pretty simple proof, but I'm going to make it a little bit lengthy, kind of describing the thought process through a proof. Okay, so I need to prove that this set on the left-hand side is equal to this set on the right-hand side. And remember how we do that? I'm going to describe how we're going to make that proof happen. We will show, or if you want to say we will prove, you can say that as well. We will show, one, that A intersect B union C is a subset of the right-hand side. And we'll show it the other way as well. Number two, we will show that the right-hand side is a subset of the left-hand side. And I'm going to give you a little bit of exposure to another way of writing this. A subset can be written the other way as well. I just want to expose you to that symbol because you may see it in the textbook. So I'm going to write A intersect B union C, and then the backward subset, A intersect B union A intersect C. So this really means, number two means the right-hand side is a subset of the left-hand side. It's the first time we've seen it written that way. You could also say, I rarely use this term, but the left-hand side is a superset. The left-hand side is a superset of the right-hand side. The right-hand side is a subset of the left-hand side. All right, well, let's do a two-parter. Let's show the first part. To prove that this is a subset of this one, all I need to do is say, let X be an arbitrary element of this set. And then deduce, step by step, that X is also an element of the right-hand side. All right, so I'm going to assume that's true. If X is an element of A intersect B union C, it's an element of the set on the left-hand side, then what does that tell us? Intersect means it's in both of these. Remember, intersect, the little word that goes with it is and. Then X is in A, and X is in B union C. Okay, and I'm going to make in parentheses, I'm going to say that this, remember what union means, this part here in parentheses I'm going to write, that means X is in B or X is in C. One of those is true. So this statement here tells us that X is in A. And it's also in B union C, which means it's either in B or C. So I'm going to break this into two cases. If this part of it is true, and then I'll say, okay, well, that may be false, which means this part of it is true. If X is in B, then I can say that without proving this, I'm going to say that, let's see. Well, actually, this is very simple. I was going to make it harder than it needs to be. If X is in B, we already know that X is in A, right? So X is in A. If X is in B, then X is in A intersect B. It's in both of them. Otherwise, and I could say if X is not in B, and maybe I will. If X is not in B, then X is an element of C, because that's this. One of these has to be true, one or both of them. So if this part is false, that part is true. So if X is not in B, then X is in C. Thus, X is in A intersect C. That means and. We know it's in A. And now if it's in C, we know it's in A intersect C. So I'm going to put down then in either case, it's satisfied. We see that either X is in this or X is in that. It follows that, and I would probably like to put 2 more sentences, but I'm just going to use 1 more sentence for this proof because I'm running out of room. Thus, it follows that X is an element of A intersect B or A intersect C, right here. That's the end of case 1. So you basically just break it apart. If X is in A and this, we showed that it means it's either in A and B or it's in A and C. That was exactly what we wanted to show. Now let's go to case number 2. We're going to assume that for case 2, we're going to assume that X is in this to prove that it's in that. If X is an element of that, then X is, remember this is an or, that means X is either in this or it's in that. Then X is an element of A intersect B, or X is an element of A intersect C. That's just the definition of what union means. It's in either one or the other. All right, well, what does it mean? Remember what we're trying to prove. We're trying to prove that it's in A and in B or C. So let's break this up. We're going to have 2 cases here. One of those is true. If it's the first one, if X is an element of A intersection B, that means that it's in A and in B. Now let's see if we can justify my next statement. Since X is in B, we see that X is in B or C. That's really an obvious statement. It might, if you were to play with it a little bit, write it down, I think you could explain it to yourself very simply. But basically, if you're in X, if you're X, if you're in the set B, you're also in B or C, because B or C means you're just in one of them, okay? So it's like saying, if you're in this set, you're also in this bigger set, when your original set was contained inside the bigger set, okay? Because B is a subset of B union C. Okay, so we know that X is in A, and we know that it's in B or C. Thus, it's in A, and it's in B or C. That's true, or I should be pointing to this one. Thus, X is in A and in B or C. We're not done. We have just one more little sentence or 2. This was the first case. Remember, X is either in this or X is in that. Well, if X is in this, A intersect B, we proved it. Otherwise, X is in A intersect C. And the remainder is just going to be very, very similar to what we did above. Okay, if it's in A intersect C instead of A intersect B, then otherwise, well, maybe I should use the word and there. Otherwise, X is an element of A intersects C, and so X is in A and X is in C. But X in C implies, I'm using a little shorthand here because I'm running out of room, X in C implies that X is in B or C. So we know that X is in A, and we know that X is in B or C, so we're done. Same thing. Therefore, finish off the proof, I like to use the word therefore. X is an element of A and B or C. So case 2 actually got broken into 2 subcases of its own. We had to break it. Case 2 says that X is either in this or that. We could call this subcase A, and I don't want to use A, subcase I and subcase J. So if this is true, that means we're doing subcase I. Otherwise, if that's false, then that would be our subcase J. We have a 2I and a 2J maybe. And then this symbol for the end of the proof.